Hi everybody, welcome to my first video on axial bars. So the definition of an axial bar is basically a member, let's call it, that takes its loads parallel to its axes. Alright, usually a symmetrical axis. So let's get a drawing of that because that sounds like a dumb definition to me, too complicated. So here's a bar. And here is its axes. There's the one and the other. Where would the other be? Well, the other has to be right here, right? There we go. And we said it takes loads parallel to its axes. So, that means loads here. Load, 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 a load. Something like that. Now, you almost will always see like these type of loads on this way. Like you'll never see that it's like very wide and like small. So usually you can say the length is greater than the thickness. Alright, so basically something that's long and that's being pushed or pulled. Alright, now there's lots of different types. I pre-drew all the mountings here. So the first like straightforward, that's the almost obvious type that we've seen before. Just a straight bar. And it's being pulled with a load P, like that. Alright, it's about the simplest these get. The next one that you could think of is like the same bar. And now you have different loads placed at different locations. So you have like here, P1, and here somewhere, P2. And why not? Let's just smush it up here with a P. There you go, right? So a load with like discretely placed forces. Alright, now we can also take those forces and kind of like apply them in like a sort of continuum, like varying as like a function of distance. So here, we can draw like a distributed load. So you can imagine a different type of physical situation. This could be like even the weight of the bar itself is like a distributed load, or you can imagine like, ice caking on here, like slowly getting bigger, the weight or the ice or whatever is like a function. And it's given, some sort of like Q as a function of distance. Let's just call that X for now, where X starts here. Alright, there's some applied load. And then we can also, start changing the areas. So, we can have this type of situation. We have a bar like this, two different cross-sectional areas being pulled, right? And we can also put this in a continuum, right? So we can have like a tapered sort of bar like this. It's not too hard to imagine, right? Where the area is some sort of function of, well, let's just call X again, right? It gets bigger. The more you go this way, smaller you go that way. So it's going to react differently than a bar that's of the same diameter. And then we can also imagine a bar was made out of more than one material, right? So let's just call this here material 1. And this, of course, material 2. Like we said in one of the previous videos, different material have different Young's modulus, right? So this one here, has a Young's modulus. Let's call it 1. This has 1, 2. Alright, so these are the basic types of bars, and you can pretty well combine these in any way you want. They can get pretty complicated, lots of fun. Alright, so let's just get into some real world examples because, well, they're the most interesting and the most fun to talk about. So I got some pictures here for you guys. This is the first one here, an oil drilling rig. Alright, you gotta love the oil. And this one here, you got to design this like bar here. It's basically an axial member for like a bunch of different things, right? You got the temperature, increase, decrease as it goes in the ground, and of course this like weight pushing down. You also got impact loading because you're like jamming it in the ground. All right, all these different things you got to take into account when you design, something like an oil drilling rig. All right, next example I got here. The Support Man Bridge. So this is one of my favorite bridges. I go to the University of British Columbia, so I drive over this bridge a lot. It's pretty impressive. And there's many axial members in here you can kind of spot out. So the first obvious ones are the various columns here, right? They're all taking loads somewhat, their own loads, the weight of like the above bridge, right? These two big columns are taking the load of like all of this via the cables, right? And also not so apparent axial member are these cables here, all right? Because when you stretch a cable, it behaves like an axial member, right? You can't put a cable in compression unless it's like -50 and you're in Yukon or something. All right, so lots of axial members, and it looks really cool. And of course, I've got another example here. You guys can probably already guess what this tower is. I can't fit the whole thing on the screen. Yeah, it's the Burj Khalifa, right? This is like the mother of all skyscrapers. It's just an amazing piece of engineering and art and everything, right? So this got an incredible amount of axial members. It's got 330,000 cubic meters of concrete. I mean, that's just a lot. And in that concrete, there's about 61,000 tons of steel. So all of that are being compressed, tension, wherever you are in the building. And there's a temperature decrease from like the bottom to the top of about 6 degrees Celsius. So you can imagine like it's really hot down here, so the metal's expanding, and up here it's like relatively cooler. So it's like, shrinking up there. So you got to take all these things into consideration. I've got to say the most interesting thing for me is the foundation of this thing. It looks like this. And basically what it is, it's like these three things here, buttresses we call them. It's basically like, a concrete structure that like supports another one, like a common buttress you might see like against like a wall would look like this, concrete. You got a load on here, and that's like supporting the wall. And this is a hexagonal core, so we call this a buttressed hexagonal core. And what's kind of interesting, I think, is this kind of looks like a flower. And in the Dubai, where the Burj Khalifa is, there's a flower called the Hymenocalypus. I could be saying that wrong. And it looks like this. It's like a desert flower, so they designed it after that. All right, that's pretty cool, right? But anyway, the foundation, because there's no like granite there or anything, they have to build it on the sand. And this thing is probably pretty heavy, so they got to support that somehow. And they do that by putting piles in. All right, so a pile is an example of an axial bar, really. All right, so if we draw a pile, there we go. It's being pushed down, presumably by some force. And it's going to react by not just like putting a force up here, but by like the friction on the side, like a skin friction. Alright, and that's from like the sand. You can get a pretty high friction. You also do it in like lots of muddy areas and deltas and things like that too. But in the Burj Khalifa, there's 192 piles. So they're situated all through here. I think there's a higher density of piles in the center. And each one of them is 43 meters long and has a diameter of 1.5 meters. All right, so just a lot of concrete. And that supports the weight of this entire tower. All right, so that's all the examples I got. I just love, practical examples because it gives you an opportunity to practice the skills you've learned. Doing these toy problems and allowing you to see what they actually do in real life. Alright, I'll see you guys in the next video, and we'll start to examine these things in more detail. Thanks so much.